Can I thank you all so much for joining us today, and really deeply thank you for giving us 12 extra minutes of your time to work through all of our technical challenges. For those of you that I haven't met before, my name is Claire and I'm the CEO of the Smart Creek Cooperative Research Centre. We're very pleased to be working with the full concrete supply chain, research environment, the government providers. Here we are popping everything up in the background. Thank you. Thanks for that, Natalie. Very pleased to be working with the full concrete supply chain towards pathways to decarbonisation for this sector, leveraging collaboration, innovation, and some really fantastic sectoral engagement. So today we wanted to have a conversation with you about pathways to new performance testing as a way to really enhance our ability to adopt new low carbon concrete products quickly, but also with a real understanding of the risk and the compliance and really get that real certainty about how these products work. So we've got a fabulous panel for you today to talk about various aspects of this question of performance testing. And before we dive into that though, I'd like to acknowledge the fact that I'm joining you today from the lands of the Gadigal people of the Eora Nation. I'm very pleased to pay my respects to elders past and present, not only here on Gadigal land, but the lands on which you're joining as well. And I'd also like to extend that respect to any members of our First Nations community that are joining us online today. It's wonderful to have you here with us. So we really do want this to be a very interactive session. So there's a couple of options for you. Obviously, there's a Q&A function and a chat function that we're very grateful that all of you have reached out to say there have been some technical problems already. So you're clearly across how to use that function. But as we're going, please feel free to pop any comments or questions into either the chat or the Q&A. And we've got a couple of members of the Smart Creek team online that are going to help us to moderate that. And we'll also have an opportunity to bring all the panelists together at the end to answer some of your questions. But we also really want to hear from you on your thoughts on this topic. And so we've popped together a little questionnaire that hopefully you can fill in while we're having this conversation. If you could take out your smartphone, if you're working on your computer at the moment, and scan this QR code, it's going to take you through to menti.com. And it should hopefully take you straight through to the questionnaire. But if not, you can enter the code 42717505. And there's going to be a series of questions there so that we can get some information from you about what your thoughts are on this topic and how we really advance this question of new performance testing to help with the adoption of new low carbon concrete products. So without further ado, I'll move us on to the session where we again hear from Henry, and apologies again, Henry, that you're starting your conversation again. But it's so wonderful to have you joining us. Thank you for your time. Henry is the engagement manager at Standards Australia and is responsible for managing engagement and strategy for the building, construction, water, waste and timber sectors at Standards Australia. So Henry, over to you.
Thank you so much, Claire, and it's lovely to be here. Thank you so much for inviting me. All right, I'll try and keep this short and sweet after our technical glitches. I have brought some slides with me, so bear with me. Hopefully I'm now sharing. So I just wanted to give you a bit of an overview of who we are and kind of what we're doing, and particularly, you know, in terms of this important space. So we've been around for over 100 years. We're Australia's peak independent, non-government standards body. So we develop standards. We are very active in the international space, and we like to harmonise our with our international work. So it's really important to kind of let you know that our work is actually driven by industry. We don't sort of just magically put our fingers in the air and decide what it is that we want to be working on. Our portfolio of work is actually driven by industry. It's driven by our stakeholders, and we are a trusted partner of government, industry, and the community. So we work very closely with the Australian Building Codes Board in developing standards for use, particularly in my area, the building sector. So what do we do and what don't we do? So we facilitate the development of standards which provide net benefit to the Australian community. We don't police the standards. We don't make laws. We can't affect regulation, and we don't certify products or systems. Our standards law. No, a lot of our standards are actually voluntary. So I work in the building space. A lot of our standards are, of course, referenced in regulations. So many of our standards are actually referenced in the National Construction Code. And when that happens, the use of those publications does become mandatory. I wanted to talk a bit about our proposal process and who can submit proposals to develop new standards or publications or revise them. The short answer is anybody can submit a proposal for new work. It doesn't matter where that comes from. If someone identifies that something needs to happen, then send us a proposal. So we're becoming more active, as you can imagine, particularly in the sustainability and you know, we're really sort of pushing in the decarbonisation space. And that's coming from the industry. In terms of sort of what we need to look at, we need to look at the problem statement. You know, what are we trying to fix? What are we trying to do? We don't want to develop standards or other publications just for the fun of it. There must be a purpose behind it. And then we need to look at, you know, what's the scope of the work? What does that look like? And we'll look as many of the specifics as we can before we start the work to kind of iron out as many of the problems we can before we get started. We'll also look at, you know, who's going to do the work. Is it going to be you know, our traditional technical committee? Is it going to be a lower consensus document for one of our speed to market solutions where we might just get individuals to work on that, or a small number of individuals? And as I said, everything we do is about the net benefit for Australia. So it's also important for us to get support from a wide range of stakeholders. When we send out proposals for public consultation, we want to talk to as many people as possible, whether they're behind it, whether they think it's a great idea or whether they think it's a terrible idea. Is this going to affect the users adversely? Is this going to have a terrible impact on manufacturers, for example? Are people not going to be able to afford to implement these changes? So it's really important for us that we do actually have conversations with a number of our stakeholders and look at both sides of the coin. I also just wanted to touch very briefly on our development process and demystify it a tiny bit. So, as I say, anybody can submit a proposal. Once that goes through its approval process, we'll then assign a project manager to it and we'll kick it off. That drafting could take some time, depending on whether we're kind of going down our sort of our faster solutions or whether we're going down our traditional standards pathway. So that could take could take 18 months, a couple of years, and then we've got a public comment phase, which is 9 weeks, and that's the opportunity for the general public to get involved and give us their thoughts and feedback as to whether we've been doing a good job with that working draft before we publish it. We want to flush out any surprises before we publish. The committee then will have a 2-week ballot process, and then we publish. I've made it sound very straightforward, but that's the general gist of it. And that's generally how our traditional pathways work. But then we have our, dare I say, our speed to market solutions. All right. So as I said, anyone can drive the development of a standard, and we've got a number of pathways which aim to speed up some of these solutions. So handbooks and tech specs are a great pathway for getting documents out, a bit faster than our traditional Australian standards. Our handbooks are what we call lower consensus, and that means it doesn't need to go through as much of a sort of a rigorous process as an Australian standard. It won't need to go to peer review unless we think it needs to. It'll only go to public comment. It'll go to peer review, which is a lot more informal, and that's where the experts will provide their thoughts and feedback on it. The same for tech specs. It's a lower consensus document. You'll have a small group of experts developing that piece, and it'll also go to a limited peer review. We've also introduced interim standards, which are much speedier than getting a full standard developed. But it's very important to note that these tend to be for projects where perhaps the idea isn't fully formed. Perhaps we haven't got total agreement on that work. It does allow the market to look at what work's been done in that space and provide their feedback. And the idea of interim standards is that one day that'll become a proper grown-up standard. So we also have we've got a new process around international work, which is where technical committees can opt into automatic adoptions of international standards as Australian standards, unless there are objections. That's cleared the path a lot in some of our committees to move work along far more quickly. And in that regard, we also have a fast track amendment process, which we've recently brought in. This is a very a very quick way of getting amendments out to market. There's no drafting time. The changes are marked. So this will be, for example, for correctional small changes. The corrections will be marked straight into the proposal and will go straight to the committee for approval and straight on to public comment to publication. It's worth noting that our AS 3600 supplement amendment was a fast track amendment, so that went straight to publication without any need for full drafting life cycle. So it's kind of a game changer. We want to speed things up, and we've listened to feedback we've got over the last few years where we need to be faster, we need to be better. And particularly when we're playing, as I say, in this space around wanting to to move across the decarbonisation journey, to make things more resilient, to make things more sustainable, we have to be more mindful about, just being better and being fast out to market without removing the robustness of what make our publications so important in the Australian community. So just worth flagging some of the pieces we've got kind of going on at the moment. They're all in various stages. So as I said, we had the fast track amendment. So that was published quickly for the correct interpretation for the intent of AS 3600 2018 and allowing the community to realise the benefit offered by 600 MPA steels, potentially improving sustainability and construction costs. We've got the big ones, the AS 3972 general purpose and blended cements, where we're looking at the different types of low carbon cement types being used, and the use of different pozzolans. So that's a very important piece of work. The AS 3600 concrete structures is also a massive piece of work. None of this is straightforward, but we're all sort of moving along as quickly as we can. So that includes looking at potential inclusion of provisions for geopolymer and alkali activated binder concretes, sustainability, use of waste materials and review of the existing structures. And then of course we've got AS 1316 masonry cement. Now this one's pending while we look at committee capacity, but this one's around reducing the clinker factor in masonry cements specified in 1316, and to look at the limitations on SEM content and type provided for masonry composite cements. That's all around clause 4.2. It's also worth noting some of the work that's been happening in other areas. So our bridge code, BD90, which holds a very big place in my heart. They've been very busy, and what they're working on at the moment is their ultra high performance concrete. That will be part 10 of the AS 5100. They've been very busily mindful of how to do things better when it comes to concrete and in hand with sustainability and also resilience in that bridge space. So I just wanted to kind of give a bit of a shout out to that committee and the work we've been doing. There's a number of things that we've been doing in a number of areas to sort of work on the decarbonisation journey, but it's also worth pointing out that none of it is straightforward, and I'm sure I'm not telling you anything that you don't already know. Where I think there's a lot of goodwill and a lot of engagement and enthusiasm to move us all in the right direction towards sort of net zero. But of course, nothing is ever plain sailing. So we do what we can in order to facilitate the development of these standards in as quick a way as we can. As I say, without sacrificing the robustness of what we're doing, because at the end of the day, what we're doing is for the long haul in the Australian community and in the built environment, and we're just looking at the bigger picture. So that's my take on what we've been doing. I'm going to. I think I have I stopped sharing? No, there we go. Stop sharing. So hopefully I haven't gone over time. That's us in a nutshell.
Perfect. Thank you so much, Henry. That was a really great overview. I think it beautifully sets the scene in terms of how the evidence that we're creating through these performance tests is then actually used through that whole process of review, and then finally the publishing of standards. So yeah, really, really appreciate that overview. Thank you. So I'm really pleased we'll move on next to our next speaker and get through it to try to bring back those 12 minutes that we lost. I'm really pleased now to introduce Marjorie Valix, who I'm sure is known to many of you on the call. Marjorie is a professor in the School of Chemical and Biomolecular Engineering at the University of Sydney. We're also very pleased that she's leading a number of the projects within the Smart Creep CRC. She provides a lot of great technical expertise and professional advice around testing, research services, the community, government, industries. And so we really felt like she was such a fantastic person to help us have this conversation about the pathway to new performance testing. Marjorie, before I quickly hand over to you, I can see your presenter screen, not the presentation itself, but over to you, and thanks for joining us.
Is that better?
Yes, perfect. Thank you.
Great. Thanks, Claire. I'd just like to talk to you a little bit about what we had been doing as a case study from the water utilities in terms of trying to develop a regulatory framework for approval of sustainable and fit-for-purpose cement or concrete materials. So I'd just like to also acknowledge James Gardner and James Goody from the Water Services Association of Australia, who've actually supported us in developing this framework. I guess the challenge for us, as we already know, is that a low carbon concrete is going to, I guess, consist of alternative type of cementitious material, so including geopolymers, calcium aluminate cement, and also blending OPC with various type of SEM materials, which may include a variety of different types of waste. So the challenge there is then how do we actually approve these materials for use, considering the that we don't have many of the performance, I guess, data associated with these materials. I guess the work that we've been trying to do is really moving towards or moving away from prescriptive to performance-based specification. So what's needed to actually develop this essentially are, I guess, various things. One of the important aspects is the cross-industry collaboration across the value chain. That means actually taking all the way from the people who actually manufacture the cement and concrete, all the way to the end users, to the applicators, to the pipe manufacturers. And that's really needed because you need to have this knowledge sharing and also to take the risk, and also as much as possible to have everyone who's going to be involved in the process to be sitting in the same table to internalize the risk, so to speak. The other aspect is actually trying to, I guess, define the unique performance that are actually required for this material. And I think this is going to be very specific for the different industries. And in particular, I'd like to take this opportunity to show what the requirements are, for example, for the water utilities in their application in sewer and also water application. And the other aspect, of course, is the importance of R&D, which is obviously what universities do, and essentially trying to tailor specific carbon solutions that needs to meet the requirement of the industry. The other aspect that's really important is the validation. Validation is very important to ensure that the actual performance is actually achieved. And then finally, of course, is the regulatory framework to make sure that we can actually implement this. Now, an important aspect of developing a performance-based specification is not only about making sure that it actually performs. The other aspect that is also important is to ensure that we can actually also capture the important aspect of the embodied carbon, because here we are really trying to develop not just a cementitious material that will perform, but we also need to make sure that obviously it meets the embodied carbon requirements that we're trying to reduce, and also the cost issues. We need to recognize the embodied carbon is not just in the material itself, but it also involves in the construction of the materials and the subsequent repair and eventually the end of life of that material, how we're actually going to deal with it. So with that in mind, I'd like to just, I guess, showcase the previous work that we've done, which is funded by the Cooperative Research Center project. And it was titled the Smart Linings for Pipes and Related Infrastructure. Okay, so we did a lot of things here, but one of the important things that we needed to actually develop are the regulatory framework for approving the materials that would eventually be used for protecting these particular assets. So we were working really with a series of cementitious material, all the way from alkali activated materials or geopolymers, all the way to calcium aluminate cement. So the question was, with this range of different type of cementitious material, how do we determine which is suitable, and how do we determine how to actually select the one that would be appropriate for the application? So this is essentially the regulatory framework that, or the proposed regulatory framework that we've come up with. So in terms of the performance-based specification, we think of it as a process where it's really a specification and also the validation aspect. So in terms of the performance-based specification, what we've developed there are a series of product specification, again, referring to the different type of cement materials, very similar, I guess, to prescriptive, but also is specifying the requirements that needs to be met, including, of course, the codes of practice and the classification of the corrosion risks under which each of these materials are going to be applied. And that's quite different from, I guess, how we have actually specified cement or concrete materials for, say, pipe manufacture in this space, in that we actually moving away from simply considering the corrosion risks, for example, censure, as being highly aggressive, but to trying and trying to divide that according to the actual different risk factors. And what that actually delivered are things like the performance requirement, including test methods and acceptance criteria that would be actually suit those this particular corrosion risk. There's also obviously qualifications and certification for the production facilities and personnel that goes into that, which we didn't really work with, but we know that it is also part of that specification. So how do we know it works? Well, part of it obviously are validation. Okay, so typically the best way to validate is just test it in the field. So often it would be a long-term process, also very expensive. But again, just making sure that it actually reflects the classified corrosion risk. The other aspect that we are also now in the process of developing and getting approved is the series of accelerated corrosion resistance tests that determines the suitability of the cement or concrete materials against the classified corrosivity. And then as part of that, what we aim to do is to establish also the service life of that of those materials, again, against those classified corrosivity. And then finally, to also include there the LCA and LCC, because we need to obviously understand that if we are going to work with low carbon material, we need to make sure that we are delivering a low carbon material, but also we understand, for example, the life cycle costs associated with the use of that material. So essentially, as part of this program, we've developed two standards. One is for alkali activated materials and also geopolymers and calcium aluminate cement, the codes of practice, and also a decision tool. Now, I'd like to just highlight a couple of things that I guess were probably important in developing this performance-based specification. One is the corrosion, the classification of the corrosion risk. What we really needed to understand was to enable us to ensure that we have a fit-for-purpose solution or fit-for-purpose concrete solution. We really needed to understand the relative risks associated as a result of corrosion that is introduced by the different environmental factors. So in this particular case, the sewers. So in order for us to do this, what we've done is we first selected the environmental factors that we know contributes to the corrosion. We then did a series of environmental surveys, followed by condition assessments of the assets under which these environmental factors are present, then followed by the classification of the corrosion risk, and then the validation of the corrosion risk itself. And what we have developed essentially are, this is a simplified version of the different classification risks associated with the different environmental condition, and also the actual impact on the corrosion of a normal OPC. And to validate that, what we've done is we then installed a series of alternative cementitious material in this environment. And then we then also measured the relative corrosion. And this is an example of one material that we have installed. And so we could see here that we do have different levels of corrosivity or corrosion rates attributed to depending on the different aggressiveness. So C1 being the lowest, the least aggressive, and C5 being the most aggressive. And essentially that validates that the classification that we've developed for OPC also works for other types of cementitious material. So on the basis of that classification, what we have then done is try to propose a series of way of validating the corrosivity of the different mortars. So this is a series of accelerated corrosion tests that essentially mimics the corrosion risk that is available in sewer. So the scope of this test essentially is to actually assess the durability of the different cementitious material as a function of those environmental conditions that could either be as a result of MICC and also soil corrosivity. The other aspect is that we do want to determine whether the materials themselves are fit for purpose. That means they will survive that environment, but also we wanted to understand the required service life of that material if it was actually applied in that environment. So the evaluation method itself involves essentially imposing or subjecting the materials to a series of accelerated corrosion tests that mimics the classification risk conditions. And then the acceptance and the criteria for the acceptance criteria for the material is established essentially by comparing the corrosion results for that material against the performance of OPC under a similar accelerated corrosion test, and then calibrating that against the OPC's established long-term performance in the same real environmental condition. Now, because we have lots of data on the OPC that has been subjected over the years from, for example, 17 to, let's say, 80 years, we're able to use that essentially to benchmark the behavior of alternative cementitious material compared to OPC. And we therefore use that to evaluate the acceptance of that material. So in terms of validation, it just shows you, for example, a high-end corrosivity test where we compare the service life of particular asset or particular material and comparing that to the service life we would predict using this acceleration corrosion test. And so at the high-end corrosivity, so this represents, by the way, different types of cementitious materials, OPCs, and different alternative concrete. So I haven't tried to distinguish one from the other. And then this one is part of more a low corrosivity sort of comparison. So we could see that it's not a perfect sort of fit, but we do have a reasonable fit that shows us that at least the trends are going the right direction. Okay, so question is, oops, sorry, what's next? So obviously a lot of this work that we've done before are based really on cementitious materials and mortars. And so the next phase of our project is a project that we're actually undertaking as part of the CRC SmartCrete, which we call Fit for Purpose Concrete. So this is a 4-year project which will examine various types of low carbon cementitious material, also augmented with waste, to try and use it for construction. So the test case will be for using it as to manufacture access chambers, pavements, and roads, and also as part of cement mine backfill. And what we're doing is we're partnering again with a range of industries, which we know will have involvement in the whole value chain. And the idea again is to ensure that we capture the knowledge sharing and also to understand the particular risk and concern, and also to make sure that we have an early adoption of the products themselves by including the end users, such as the water utilities, the transport and roads industries, and also the mining industries. Okay, thank you.
Thanks so much for that, Marjorie. It's so fabulous to see that direct example of the development work that you're doing in terms of new performance testing, and then to be able to see how that's being published and shared and kind of, you know, being promoted in terms of that adoption. So yeah, really, really pleased to see that, and the work that you're doing in the water industry there. It was fabulous. So our last speaker today is Josh Tapas. Josh is a materials engineer at GHD, but again, probably well known to many of you on the line. She is also the president of the CIA Next Gen community, so very, very well known across the concrete sector. She's an experienced materials engineer with experience across material characterization equipment and proficiency in cement and cementitious materials. Josh has very recently finished her PhD working with SmartCrete's very own Professor Voot Sirivavattanon, and she was focused on alkali silica reaction and major durability issues in Australia. So Josh, thank you so much for joining us on the call today.
Happy to. Let me just share my screen. Is that?
Perfect.
Does that work? No?
Yep, we've got it. Thank you.
Is it on a slideshow or?
Yep, you're in presentation mode. We can see it.
Okay.
Great. Thanks, Josh.
Okay. Okay. Good morning, everybody. So I've actually been nominated to talk about the testing of SEM to mitigate alkali silica reaction, but I think really the bigger issue is with the entry of low carbon concrete into the market, the new generation of low carbon concrete. How can we be assured of the long-term durability and that they can actually meet the design life? So ASR is one of the major durability issues. And I think before I go to testing of SEM, I'll give a short overview of alkali silica reaction. So this bridge is a very good example of a structure suffering from alkali silica reaction. You can see here the signature map crack appearance because of ASR. And ASR happens, for those who've never heard or not very much familiar, it happens when you've used our active aggregate in the concrete mix. Reactive aggregate means it has an unstable form of silica that has a tendency to dissolve under the high alkali pore solutions of the concrete. And the dissolved silica in the concrete now then starts to interact with other ions present, such as calcium, forming a product we know as alkali calcium silicate hydrate. Now, this ASR product, once it accumulates, has a tendency basically to result in concrete cracking. Once concrete cracks, therefore, it becomes prone as well to other deterioration mechanisms. Now, ASR preferentially happens in locations that are very close to water, and therefore susceptible structures are bridges, dams, as well as marine structures. Therefore, since ASR is primarily caused by the use of our active aggregate, the main way, the best way to actually avoid having to deal with ASR in the future is to avoid using the use of our active aggregate. Then how do we test the susceptibility of the aggregate to alkali silica reaction? So just to say as well that ASR damage can manifest in decades after a structure is built, 20 years or more, right? But we don't have that long of a time to actually wait. So we have to know now before we actually use the aggregate whether it can have a potential for alkali silica reaction. Therefore, what we do is we use accelerated test methods to assess the susceptibility of aggregate to alkali silica reaction. And these test methods we use, as you can see from the screen, we have two in Australia, the accelerated mortar bar test and the concrete prism test. Basically, both test methods rely on increasing alkali concentration as well as storage temperature to accelerate the reaction. And then we plot the expansion of the system with respect to time to assess basically whether we have a reactive aggregate or not. Right? So ideally, we don't use a reactive aggregate, but in cases that we don't have the luxury and we have to use them still in the concrete mix, what do we do then to mitigate? Now, mitigation of alkali silica reaction involves the use of supplementary cementitious materials. So this has been known for a very, very long time. The question then is, how much SEM do we actually need to mitigate alkali silica reaction? Now, if we're talking about conventional SEMs, fly ash and slag, who's been around for several decades, we know that talking about conventional chemistry, we need about 25% fly ash or roughly over 50% slag to mitigate alkali silica reaction. The more active the aggregate, though, the higher the dosage of SEM required for mitigation. And therefore, we still have to test to actually be sure of the dosage required. But we already have a lot of documented cases, over 50 years or so, structures built that survive well, even with the use of reactive aggregates when we have SEMs in place to mitigate. Now, the plot you see is a sample, basically a sample accelerated mortar bar test expansion data. So it tests up to 21 days. Basically, you can see with increasing levels of SEM you put in the system, you get a decrease in the expansion. And that means that equates to mitigation, which means SEMs are working well to mitigate. You can also see here very clearly that not all SEMs are the same in mitigation. Slag, for example, would require more than fly ash, okay, which is good, actually good for our low carbon concrete initiative in any case. But the bottom line is not all SEMs are the same. Okay, now the next question perhaps is, how are we sure that the testing results are reliable? Again, I think Professor Marjorie has already mentioned her presentation. The only way, the best way, is really to do a long-term performance test, okay, field data. When we're using accelerated test methods, say you're having a 21-day test result, and you're guaranteeing that your structure will not suffer from ASR for the next 50 years, if your design life is 50 years, for example. Bridges, if you're talking about 100 years. And basically what you're saying is that, oh, I can test my concrete, my mortar in 21 days, and I guarantee you there's going to be no problem. So the accelerated testing methods really does not mean much without correlation to long-term data. So this paper was published about 2 years ago, where we looked at long-term data over 20 years, actually now over 30 years already from recent updates. Long-term data of ASR concrete samples in the UK and in Canada. Unfortunately, we don't have a field exposure site in Australia. And probably that's because we don't have as bad a case here as what we have in other parts of the world. But nevertheless, this data are very valuable and the only data we could actually use to benchmark. And what we found is that the accelerated test methods actually have very, very good correlation with long-term performance data. In fact, the Australian test methods with their current test limits are conservative in comparison to the American counterparts. So the Australian test methods are exactly the same, basically, as international equivalents, except we have a much more conservative test limits. And what we found is ours even correlate better. And in fact, AMBT, although heavily criticized to be a very aggressive test method, work better in terms of determining the dosage required for long-term mitigation of alkali silica reaction. I guess now the question then becomes, to me, that there's no question we should be able to extend the test methods for aggregate reactivity to SEM mitigation in ASR for assessing the efficacy of SEM mitigation. Worth mentioning as well, because I'm talking about testing of SEM, but actually we don't have a dedicated standard at the moment. We use the standard for aggregate susceptibility, but we don't have a dedicated standard. So that's in process. I think has undergone several reviews in the last few years. Hopefully it should get approved soon. So hopefully that paper was actually written to support the extension of the existing test methods for SEM mitigation. So the next question then comes, would the test methods work to test other type of low carbon binders? I think we've already come a long way forward. The new generation of SEMs, I think, inevitable, because moving to the low carbon space, net zero by 2050, we know that the SEMs we're using, fly ash and slag, are byproducts of industries that may not be present or with processing that may change in the future. Slag comes from steel. We're moving towards green steel. We may not have access to the same slag chemistry in the future. Fly ash comes from coal-fired power stations. So I think in the next 20 years, with the closure of the coal-fired power station in Australia, we don't have the same fly ash chemistry anymore, maybe other types of ashes, okay? But anyway, the triangle on the right basically shows us a typical chemistry of the traditional SEMs. And if we look at AS35A2.4, this is actually a good step forward already. So we have a standard that actually allows us towards the use of manufacturing pozzolan. Well, the key term here is still a pozzolan, which means we're still not allowed to just chuck in anything in the concrete. So you just can't replace cement with anything. So there are still guidelines. You still need a level of fineness, a level of alkali concentration, a level of SEM chemistry that you have to meet to be able to first be used in the concrete. That's the first step. And if you look at the standard, the biggest requirement is that whatever you put in the concrete should not result into detrimental effects to both the fresh and hardened properties before you even go to durability. And just pozzolan, by the name itself, is very much associated with aluminosilicates. So I think the new generation of SEMs will still be within this region. Similar to the traditional SEMs, we have potentially a different type of chemistry, different types of other elements associated in there, but still will be a type of aluminosilicate. So I don't see a reason why we cannot extend the existing standard toward assessing the new generation of SEMs for efficacy and mitigation. The critical thing, though, is understanding the chemistry of the SEM, understanding the test method, and what it does to the system. Now, alkali-activated binder geopolymers, I think, a more controversial topic because SEMs are established known to mitigate alkali silica reaction, but alkali is known to aggravate ASR. So basically, one is you're almost expected that one would offset the effect of the other. But again, we've had a good move in this space. So there's SAPS 199, recently published, with the design of geopolymer and alkali-activated binder concrete structures. Now, geopolymers, a very, very complex chemistry. Definitely, this is a very good move towards performance-best specifications because geopolymer, you can make different SEM combinations, different types of activators, different alkali concentrations, almost impossible to capture it in a prescriptive form of a standard. So I think we've made a good move on this one. Looking at this particular standard on ASR, like any other state guideline, if you can avoid not using a reactive aggregate, don't use one. If you have to, it differs back to the accelerated mortar bar test. The criteria, a little bit vague, but it provides an opportunity to use reactive aggregates in combination with alkali-activated binders, provided that the expansion is less than an OPC with a non-reactive aggregate, which means then your system should have no expansion at all to be considered acceptable. So I think there's a potential in there, but I think would have to be clarified in terms of expansion limits. Alkali-activated binders, I think more studies are still required, particularly for other durability deterioration mechanisms and other durability concerns. But this work by Osroads is probably the most comprehensive I've seen in terms of alkali silica reactions. If you go through this publication, they've investigated several chemistries of alkali-activated binder systems. And overall, they still demonstrate better resistance to ASR than typical cement. Fly ash-based geopolymers have better resistance than slag. Not surprising, because basically with very high levels of alkali, you're almost pushing the required silicate in the system to a higher level to be able to mitigate. So in fact, if you look at the plot on the right, it's if your slag geopolymer is about 100%, no fly ash at all, it cannot mitigate ASR. With this particular level of alkali, the 6% sodium oxide equivalent, about 10 times what you have in your cement. Again, the resistance of alkali activated binder depends on the binder chemistry and the concentration of the alkali activator. So conscious of the time, I have to go a little bit fast, but conclusions, the test methods for assessing aggregate reactivity can be extended for assessing SEM efficacy in ASR mitigation based on the paper we've published 2 years ago, looking at data from long-term field data from the UK and from Canada, where our Australian standards and test limits are even more conservative and proved to be very well correlated to the long-term data. AMBT is a quicker method, 21 days, and even provides a better way to assess the required dosage, even a more conservative dosage for SM mitigation. Is there a potential to use the test methods for assessing the new generation of SEMs and low alkali binder systems? I think certainly there's a potential to do that. At the bare minimum, at least for a comparative assessment, of course, the test limits probably will have a little bit more work into it. And again, the long-term performance data will increase in the confidence in these expansion limits. I think it's critical that we understand the test methods for us to be able to decide, basically. I think that goes for any other test methods, accelerated test methods that we'd like to apply for assessing the new generation of low-carbon concrete. Last is that not all SEMs are equal. Therefore, I think an understanding of the SEM chemistry, the pore solution chemistry, how does the SEM impact that? Because ASR in particular is very dependent on the pore solution chemistry. And the reason SEM mitigates well because it drops the alkali in the pore solution over time. It's also very critical to understand, as I've mentioned, the principles behind each testing methodology. Because if you don't understand the test, you cannot just extend. So, and I guess there's a lot of, when we don't understand things as well, you're scared to try. So I think there's a lot of understanding still required before we can adopt some of the other test methods for assessing the new low carbon binders. But I think we have everything in place and we're moving there very, very fast already. So that's all from my end, Claire. Thank you.
Thanks so much, Josh. That was fantastic. What a great overview. And so wonderful to see the fruit of your labour within your studies really being demonstrated there, and some pathways towards new performance testing, which is great. It's also lovely to see that we've got such global engagement and the fact that you're able to work with places like the exposure sites in Canada to really help validate what we're finding here in Australia as well. So we are very quickly running out of time because we spent so long at the start with our technical issues. But if I could ask our panelists to come back online, we might just do a couple of rapid fire questions because we do have some questions that have come through from the audience. Thank you so much for that. If we can't get to all the questions, what we'll do is we'll summarise those and send them out to our panelists and ask them to provide a written response, and then we'll send that out when we send the recording of this video so that we can grab those. Some quick questions then. Maybe over to you first, Henry, because there's a question here for you around biochar, but also a very easy one about how we contact standards. But if we start with the biochar question, currently, does Standards Australia have any consideration of biochar amended concrete? And the example that's provided by Elliot from the City of Gold Coast is the RMIT Macedon Ranges Shire Council trials that are being run at the moment. Is any of that work filtering into standards?
Very good question. Off the top of my head, I don't know the answer to that, but I would love to take that one on notice and take a look at that. So yes, if you want to email us, that would be great. The best email to reach us is SEM, S-E-M, as in Stakeholder Engagement Managers, at standards.org.au. So that's sem@standards.org.au. I'd be very happy to look into that one.
Yeah, fantastic. Thanks, Henry. And yeah, everyone, please feel free to reach out to Standards. Sounds like there's a great process to kick off your own standard development process. Okay, so a quick question here from Ramon. I'll just read it out. What's the technical reasoning for great correlation using SEM to mitigate ASR? If the issue is reactive silica in the aggregates, then adding SEMs is providing more reactive or amorphous silica. So how do you know that you've correlated your results and that they're accurate if you're unsure about the technical reasoning? Josh, did you have some thoughts there?
Yes, I'm just not quite sure what's the actual question really. So I think there's two parts. One is understanding ASR and understanding how SCMs work to mitigate ASR. Another part is the correlation to long-term data. So the paper actually just looks at correlation to long-term data, which we don't have in Australia. So that's why we've looked at other field data in the world to correlate the testing methods and the test limits. For example, the Australian test limit is 0.1% at 21 days. So how sure are we that if you met that test limit, you actually don't have expansion in the field? So what we did there was first correlate American test methods to the long-term performance data. And then once we have the tabulated data, we've then used Australian test limits to draw a parallel correlation. And I was like, when we looked at that, we're like, the Australian test limits are even conservative compared to American test data. So again, SEM mitigation has been in decades, for 50 years or more. Okay, so it's work. We have structures that have been built with reactive aggregates, dams that have not manifested damage because of SEM. Now, the second question, if you are asking about what is it SM efficacy? So basically, the accelerated test methods, the reason you get ASR is the alkali concentration, facilitating for dissolution of the silica in the aggregate. So that's the reason why you have ASR, right? So either you drop the alkali or you put something in there to drop the alkali. So the way SEMs mitigate is two things primarily. SEMs are known for one, microstructure densification. That's why for durability, if you look at durability specifications for anything almost, you put an SEM there to resolve. That's known because SEM, by being pozzolan, that means you get secondary hydration products over time that then densifies the microstructure of the concrete. Second is because through the formation of these products, you get alkali binding. So you draw in your alkali in the system and bound in the SEM. So you drop them over time. So I'm not sure if that answers the question, but I just captured the full.
That was really great. Thank you, Josh. And I might skip a couple of questions and just throw another one to you very quickly because that might actually be a great place to point people. So Prathap is asking, do you have field ASR data with SCMs available? So where would people go if they were looking for more information on some of your research?
Oh, I think Professor Wood may be the best contact person. She can email Smartcrete. He's the first author.
Email Smartcrete
of the paper. He was also in Canada a few months ago. So I've heard from him. So when we did the paper, it's 20 years. Actually, the recent update is over 30 years. This cements even they're using 0.9%. I forgot to mention that's 0.9% alkali content in the concrete. Australian cement, we already have a one level of mitigation. We've capped the cement limit to just 0.6. So again, we're conservative. I think Australia is always conservative compared to the world. So
yeah, thank you. And yeah, happy to connect you with Voot, who is maybe online right now. Two more very quick questions and then we'll wrap up, obviously respecting all of your time. So thank you all for hanging on. So the quick one from Andrew is, why is fly ash counted as a waste product when it should be called a byproduct? I think we can answer that pretty quickly, which is this is actually a really important definition, particularly under EPA guidelines, in that it does actually need to be classified as a byproduct so that it can be reused. So you're correct in saying that we would not technically call it a waste product, but we would consider it as a byproduct. And this one I might throw to Marjorie just as a last question. What are your thoughts in terms of Josh's presentation and how that relates to what you were talking about in terms of the manual and the specifications that you were able to publish after your project? And Josh's comments, obviously, they were about this continuous need for, the question is jumping around, I apologise, the need for establishing long-term performance through field trials. Did you have some thoughts about how that relates to your work in being able to publish that specification?
Oh, okay. So essentially, the work that we had to do had to rely on us to be able to actually, for example, classify and understand the actual environmental conditions, because that was very important. The other aspect is the access to condition assessment of various assets that has been actually on the field, which means that we have this long-term sort of data from, say, assets that have been in the field for up to, say, about 100 years. So having that kind of data, we're able to use that to benchmark against the actual performance on the accelerated corrosion tests. And we use that essentially to determine whether, for example, if the concrete is behaving in a certain way in our accelerated corrosion tests, we're able to compare that to the performance of alternative concrete. And knowing the performance of OPC in the field, we're able to then sort of use that as a way of benchmarking the results.
Fantastic. Well, fantastic. Thank you so much. Hopefully we've managed to get through all of your questions. If you have more questions, please feel free to send them through to info@smartcreekcrc.com.au. We'd be very happy to get you in touch with panelists to answer any further questions. It's been wonderful to have you all online with us today to discuss pathways towards new performance testing to accelerate adoption of low carbon concrete products. Thank you also for putting your information into the Menti questionnaire. Unfortunately, we didn't have time to come back and have a look at those answers, but we have been looking at them in the background, and you've provided some really fantastic additional pieces of information for thought there. So we'll be providing those in some of the follow-up information that we share as a follow-up to this seminar. Thank you so much, Marie, Henry, Marjorie. It's been wonderful having you online today to have this conversation, and thank you everyone for joining us. Have a great day.